Welcome back, all of you. This is the second part to the first chapter, periodic table and trends in periodic properties. Our next topic is electron affinity. Okay, now electron affinity is basically the amount of energy which is released when a single gaseous isolated atom accepts an electron to form its negative ion. Okay, so I can represent electron affinity as, let's say, X is my element. If it gains an electron, then it will form the anion X minus 1. The amount of energy that will be liberated, okay, as a result of gaining an electron and forming a negative ion is called electron affinity. Is that clear? Now, electron affinity the unit of electron affinity is either kilojoule per mole, or it is represented as electron volt. So when we go across a period, okay, when we go across a period from left to right, there is an increase in nuclear charge, very clear increase in nuclear charge. The size of the atom decreases as you go from left to right, correct? Now, if the size of the atom decreases, okay, then the electron affinity also will increase. Okay, why? Because electron affinity is a tendency of an atom to accept electrons, correct? A small atom takes up electron more readily than an atom which is larger. Okay, now fluorine over here has the highest electron affinity. Now when we go from left to right, we see that the valence shell being filled one by one. So each electron enters the valence shell, right? So lithium has one electron in the valence shell, beryllium has two electrons in the outermost shell, boron has three, and so on. Correct? Now for fluorine to complete its octet, it requires only one more electron. Also, fluorine atom has the outermost electrons which are very tightly pulled towards the nucleus due to effective increase in nuclear charge, which is the reason why the atomic radius of fluorine is the smallest. So a smaller atom like fluorine has a higher tendency to accept electrons and form its respective negative ion. Therefore, when you go across a period, the amount of energy released, okay, the amount of energy released would be much higher by fluorine, because fluorine would readily accept an electron and form its stable form. Okay, stable ion. Now, what happens to electron affinity as we go down a group? Now, when you go down the group, what happens is the atomic radius we know clearly increases because there is increase in energy levels. Correct? Although there is an increase in nuclear charge, here the shielding effect plays a greater role, therefore making it easy for therefore the outermost electron is very loosely held in sodium. So as you go down, the outermost electron is much more loosely held as compared to the element right above it. Correct? So, but electron affinity is the affinity of an atom to gain an electron. What we are seeing here is, as we go down, the ability of the atom to lose the electron is increasing. है ना? So electron affinity decreases down the group. Okay? So electron affinity decreases down the group. In this diagram, what we see is the electron affinity and its trends across different atomic number. Okay, so over here, if you notice, from atomic number, let's say we'll take atomic number 10 is neon. When we go from atomic number 10 to atomic number 20, right, these are the elements which are present in the third period. Okay, so this is sodium. Okay, so this here is sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and we see that it comes all the way back to argon. Okay, so what we notice is that as we're going from sodium to chlorine, the electron affinity is increasing, and Chlorine has the highest electron affinity in its period. Similarly, in the second period where you have lithium is this orange dot over here. Lithium to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So again, in the second period, these 17 group element fluorine has the highest electron affinity. So in general, the trend is that as we go across the period, we see that the electron affinity increases. Okay. Our next topic is electronegativity. Now, electronegativity, like it's mentioned, it's a measure of the ability of an atom uh, of an atom in a molecule to attract electrons towards itself. Okay. Now, what does that mean? So, atoms often are bound to one another to form a compound. Correct? They are often bound to one another to form a compound. Now, these bonds can involve the sharing of valence electrons, and not all atoms in a compound will share electrons equally. So, knowing how strongly each atom will attract the electrons present in the bond helps explain the physical and chemical properties of the compound. Okay. So Linus Pauling was one of the most famous chemists, and he made a scale of numerical values that reflects how much an atom in a molecule attracts electrons. So those numerical values came to be known as the electronegativity values. Okay. Now, chemical bonding that comes from sharing of electrons can be thought of like tug of war. Okay. The atoms with a higher electronegativity, for example, between hydrogen and chlorine in the molecule hydrogen chloride, chlorine atom has a higher electronegativity. So the atom with the higher electronegativity will pull on the electrons more strongly towards itself. Which electrons? The electrons which are taking part in the bond formation between the atoms. So hydrogen chloride is formed by sharing of a single pair of electron between the two atoms. So these two electrons are not equally shared between both the atoms. Chlorine, being more electronegative, pulls the electrons more towards itself. Okay. Now, the trend that we observe for electronegativity, what do we notice across a period? Across a period, each atom having one extra proton. Across a period, when we go from lithium to fluorine, each atom gains in one proton and one electron. So the number of energy shells are remaining the same, and the nuclear charge is increasing, as we have seen in the previous slides, due to which what happens, the electrons in the outermost shells are more strongly pulled towards the nucleus. So the effective nuclear charge increases across the period. As this increases, the electrons are attracted more strongly. Because the electrons are attracted more strongly by the nucleus, this particular atom will have a higher tendency to attract electrons towards itself, meaning it has an increased electronegative value. Similarly, as we go down the group, what we observe is that the number of energy shells increases by 1, right? Because of which we see that the atomic radius increases. The nuclear charge definitely increases as we go down, but due to shielding effect, of the electrons, the nuclear charge does not, although the number of protons increases, it does not have much effect on the outermost valence electron. Because of shielding effect, as the size of the atom increases and the nuclear pull does not have much effect on the valence electrons, the atom does not have a tendency, or does not have a higher tendency to gain electrons in the valence shell. So as we go down, the electronegativity or the electronegative values of the elements decreases. So across the period, we observe that there is increase in electronegativity, and down a group there is a decrease in electronegativity. or you can see in this diagram that the electronegativity increases as you go up a group. All right. There are some values written down in this slide, and these values are the electronegativity values according to Linus Pauling, because of which he was awarded the Nobel Prize. And you can clearly see that the electronegativity value from left lithium to right oxygen or even fluorine increases, right? Fluorine has an electronegativity value of 4, whereas lithium has a value of 1. And when we go down a group, there is a decrease, but if you notice, the decrease is not that dramatic. It's very gradual. This is a three-dimensional graph of decrease in electronegativity value down a group and increase in electronegativity value across a period. So across a period, this is the increase in electronegativity value. Our next topic is metallic and non-metallic character, which will help us understand how properties of metals and non-metals and metalloids vary across or down a period. Now, the first thing that we need to understand is, what does metallic character mean? Metals, as you know, are substances which are shiny, they are lustrous, and they are malleable, ductile. They can be beaten into sheets and made into wires. They are conductors of electricity and heat. Apart from this, a metallic character is the character of or the ability of a particular element to lose electron. So metals usually tend to lose electrons and form their respective cations. So a metal has a higher tendency to lose electron from its valence shell. Okay, so the process that metals usually undergo is oxidation. Okay, so metals undergo oxidation process, and the tendency of a metal to lose electron is its metallic character. Non-metals, on the other hand, usually have more than 4 valence electrons in their outermost shell, because of which, to have a complete octet and become stable, non-metals usually tend to gain electrons and form the respective negative ions. So the process by which any element gains an electron and forms its negative anion is called reduction. So non-metals usually undergo reduction and metals usually tend to undergo oxidation. Okay, so metallic character has to do with the ability of an element to lose electron, and non-metallic character is the ability of an element to gain electron. Non-metals are most commonly known by their non-lustrous and brittle nature. Some non-metals are hard, whereas most of them are present in the gaseous state. They are usually poor conductors of heat and electricity, and they exist as molecular substances, unlike the metals, which usually exists as ionic substances. There's one more point to remember over here, is that metals, because they undergo oxidation, they behave as a very good reducing agent. Okay, and on the other hand, non-metals which undergo reduction, they are very good oxidizing agents. If we look in the periodic table, that's how we notice that when we go from left to right, we see that the elements become, the ionic form of the elements changes from the positive ions to the negative ions. That's because on the left hand side you have all the metals grouped, and on the right hand side you have all the non-metals, which form your anions. At the in between the metals and the non-metals, you do have metalloids. In between the metals and the non-metals, there are metalloid. A few metalloids are, for example, boron, silicon, germanium. Okay, they are present at the border of metals and non-metals. So as we go across a period, we see that the metallic character decreases, and when we go top to bottom, the metallic character increases. Okay, this could also be related to the properties that we have just studied a few videos ago, few slides ago. when we talk about the ionization energy, we learnt that across a period, the ionization energy increases. Because there is increase in ionization energy, the amount of energy needed to remove an electron from the outermost shell of fluorine is going to be extremely large. So it's going to be very difficult for fluorine to lose an electron, but lithium on the other hand can very easily lose an electron. So lithium shows a much higher metallic character and fluorine does not show that much of a metallic character. So due to increase in ionization energy, there is decrease in metallic character. Okay, and when we go from top to bottom, there is decrease in ionization energy because the atomic radius increases. So the amount of energy needed to remove an electron from the outermost shell of cesium will be very less as compared to lithium. So because the ionization energy for cesium is very low, to form metal, the metallic character of losing the electron is much higher in cesium than lithium. So that basically helps us to understand that this is why potassium is more reactive than sodium and lithium. If you remember the slide in our previous video, where we had seen reaction of lithium, sodium and potassium with water, we saw that potassium was reacting much more violently with water. So this is the reason why potassium reacts much more vigorously, because potassium has a much more metallic character than sodium and lithium. So potassium can readily lose the electron from the outermost shell and therefore carry out a much more violent and vigorous reaction. When we talk about the non-metallic character of elements across the period, it is very evident that when we go from left to right, the ability of the elements to gain an electron increases, which is what we learned from the electron affinity. So fluorine has a greater electron affinity, right? The electron affinity for fluorine is much higher because it forms its more stable fluoride ion by losing the energy, by losing a great amount of energy. Also because it has a very high electronegative value. Okay, because fluorine has a higher tendency to pull electrons towards itself or gain electrons. So the non-metallic character of gaining electron increases when you go across a period, and down a group the non-metallic character decreases due to the increase in atomic size. It could also be explained with the help of ionization energy, or we could actually explain non-metallic character with electron affinity. Okay, so electron affinity decreases as you go down in a group. So because electron affinity decreases down in a group, the non-metallic nature also decreases as you go down in a group. This is a summary of all the trends that we have studied so far. So down a group, the atomic radius increases, the electronegativity decreases, ionization energy also decreases. Along with that, we also see a decrease in metallic character, an increase in non-metallic character, and also decrease in electron affinity. Okay, what happens when we go across a period? When we go across a period, the atomic radius decreases due to increase in nuclear charge. The electronegativity increases, the ability of the elements to gain electrons increases in group 17 elements. Also the electron affinity increases. The ionization energy increases, meaning to remove the outermost electron, the elements in group 17 would require much higher amount of energy. Along with that, we also saw an increase in non-metallic character and decrease in metallic character. Thank you all of you.